We're going to finish up with a couple of examples of using the central limit theorem. And so we're going to jump right in here with this example. We're told that the population of men in a certain country have weights that are normally distributed with mean 172 pounds and standard deviation 19 pounds. So the first question that we're asked here is, what is x and how is it distributed? So x is our original variable of interest, so whatever it is that we are studying in this particular study. You can look back up and tell that what we're looking at here is the weights of men. And so when we look at x, realistically, x represents the weight of one given man, right? Whichever man we happen to observe. We are told in this case that those weights are normally distributed. We're told the mean is 172 pounds and the standard deviation is 19 pounds. Right? So when we move on then and we're looking at, okay, well, let's define x bar. So x was an individual weight of one man. X bar is going to be the sample mean weight. For a sample of n men. And we know that x bar is going to also be normally distributed because x was normally distributed. So in this example, we are not relying on the central limit theorem because x was already normally distributed. So if x is normally distributed, so is x bar, no matter what sample size we're going to use. The mean is still going to be 172. The standard deviation, though, remember now we're looking at the standard deviation of x bar, which is always sigma over the square root of n. So that's going to be 19 over the square root of whatever sample size we have. So we haven't been given a sample size yet. Okay. So what we're going to do here is we're going to look at an example of a question from earlier in the chapter and then a question that's more current. So this one here says in part C, what is the probability that an individual man selected at random has a weight less than 150 pounds? This one's asking us an individual man. So this is the distribution of x, which was we did in part A. It was centered at 172. We want the probability that one man chosen at random has a weight less than 150 pounds. Well, that's going to be fairly unusual. It's down here. And we can find that using normal CDF. So our lower bound, we want to go from basically negative 1 million all the way up. So we're coming from the left here all the way up until we hit 150. The mean is 172 and the standard deviation is 19. And so in the calculators there, we're going to go to second distribution, normal CDF from negative 1 million to 150. Mean was 172, standard deviation was 19. And we get 0.1235 if we round to 4 decimal places. Okay, so it's not something that we're gonna see a lot, but it's not highly unusual either. We're saying if we have a group of men whose average weight is 172 with a standard deviation of 19, that the probability that we would pick one man at random and he would weigh less than 150 pounds is 0.1235, so about 12% of the population. Okay, What we're gonna do differently here in part D is we're changing the question. So D says, what is the probability that in a sample of 40 men, the mean weight is less than 150 pounds? So we still have the same weight, but we're not looking at one man and finding the probability that we happen to get one person who weighs less than 150. We're saying that we sample 40 men from this population and they together have a mean weight that is less than 150 pounds. That should seem like it's gonna be much more unusual to you, right? Not just one man, but a group of 40 men with a mean weight less than 150 pounds. So this time we're no longer looking at the distribution of X, we're looking at the distribution of X bar. So we need the mean of X bar and the standard deviation of X bar. Well, the mean of X bar is always equal to mu, which is still 172. But sigma sub X bar, remember, is sigma over the square root of n, where sigma is the original population standard deviation of 19, but it gets decreased because of our sample size. And so we're gonna take 19 over the square root of 40, and that gives us 3.004. So we know X bar is still centered at 172, but instead of, if we were labeling increments of the standard deviation, up here those increments would be going by 19, right? So we would have 172 plus 19, plus 19 again, plus 19 again, and then minus the same thing. Now we're going in increments of only 3, right? So now when I start labeling down here, that should make 150 seem very far away. So it would have to be way down here off the page, right? If I was going in increments of 3. So I'd be at 169, 166, 163, and we still have to go all the way down to 150. So I'm just gonna kind of put some dashes here, right? Showing we have a break in that axis. And here we are down at 150, and we want that probability. Okay, still gonna use normal CDF because it's still normally distributed. We still wanna go from negative infinity, which I'm gonna use negative 1,000,000, all the way up until 150. It's still centered at 172, but the change is the spread of this distribution is much smaller than the original spread of just those weights. So our spread decreased to 3.004. So if we go to normal CDF, lower is still negative 1,000,000, upper is still 150, mean is still 172, but our standard deviation is now down to 3.004. And that's gonna make this much more unusual. It's so close to 0 that the calculator in fact tells us it is 0. It's not really, but I'll do it this way, approximately, right? If we're going to like 4 decimal places, it's 0 to 4 decimal places, right? So what they're saying is there's about a 12% probability of this occurring in one man, right? In one man weighing less than 150 pounds. But by the time we want to take a sample of size 40 men and have that mean weight be less than 150 pounds, that's essentially not going to happen from this population. Okay, and we're gonna do one more example. So this one says that the average length of maternity stay in a US hospital is said to be 2.4 days with a standard deviation of 0.9 days. And we randomly survey 80 women who recently bore children in a US hospital. So first thing here says, what is X and how is it distributed? So X is going to be the length of hospital stay. And again here, we're just looking at each value of X representing the length of hospital stay for one woman. And how is X distributed? Well, it doesn't say anything about it being normally distributed. And I think if you thought about that, it would make sense that it's not normally distributed. Because if you're going into the hospital to have a baby, probably there's a minimum number of days you can stay, which is maybe down around 1 or 2. And then depending on levels of complications, you could stay longer and longer and longer. So this would probably be a variable that's right skewed. It doesn't tell us it's normally distributed, and so we don't know, but we know its mean is 2.4, and its standard deviation is 0.9. So what is X bar? So X bar is the sample mean length of hospital stay. Again, these are for the maternity stay, and this was specifically for a sample of 80 women. How is X bar distributed? Well, this is where a case where we would be using the central limit theorem. Even though the original variable X is not normally distributed, or at least we don't know how it's distributed, X bar is still going to be approximately normally distributed. We saw that happen back in the last video, right? So here we had an example of a right skewed distribution that still had a mean that was normal. Okay, so the mean is going to be approximately normally distributed. Its population mean is still going to be 2.4. And its standard deviation is going to be 0.9 divided by the square root of the sample size, which was 80. Okay. So part C says, can we find the probability that an individual woman stayed longer than 4 days? So an individual woman means we are looking at X, not X bar. And could we find that probability? We could if X was normally distributed. We would use normal CDF. But you will remember that we didn't know how X was distributed, and when we thought about it, we said it was probably right skewed. So I'm just going to say here, no, we do not know how X is distributed. So we can't use normal CDF when we don't know if the variable is normally distributed. Part D though, Part D says, what is the probability that the average stay for the 80 women is longer than 4 days? Now I'm looking for an average and I have a sample size. I'm no longer looking at just one woman. And so that is X bar. And we know that X bar is approximately normally distributed. And so we could draw X bar having a normal distribution. Its mean is going to still be at the population mean, which was 2.4. Its standard deviation was going to be the population standard deviation over the square root of the sample size. And so 0.9 divided by the square root of 80 is 0.1006. So we know that X bar is still centered here at 2.4, but if we were labeling out to 3 standard deviations, we would only be going by increments of about 1/10. So we'd be at 2.5, approximately 2.6, 2.7. We want to know the probability that that average stay is more than 4 days for a group of 80. This is going to be very unusual. I'm going to stick it way out here somewhere at 4. And we want that probability, that upper tail probability. So we can use normal CDF. And that's because that we're looking at the distribution of x bar, which was normally distributed. So we want to start finding area at 4. That's our lower. We're going to continue upward infinitely, so we'll just use positive a million. The mean was 2.4, and the standard deviation was 0.1006. And so if we use normal CDF from 4 to a million with mean 2.4 and standard deviation 0.1006, we get this very tiny number. I wanted to do one of these so that you could see the scientific notation here. So you'll notice it says 3.1071, etc., and then you have this E with a minus 57. So that's telling us that this is times 10 to the negative 57th power. So it's putting it in scientific notation because it is so small. Because that the part that comes after the E is negative, that tells us to find this actual number, we would move the decimal place 57 places to the left. So because it's negative, the decimal would go to the left. So this is point, and then 56 zeros followed by 3107. So this is definitely approximately 0 to 4 decimal places. The precise value is 3.107 times 10 to the negative 57th, but that's so small that we would just say approximately 0.